Welcome to an example on how to find the curl of a vector field. The curl of a vector field can be expressed several ways. One way is to express the curl of the vector field f as del crossed with the vector field f, where del is a differential operator. So if we find this cross product, it would be equal to this 3 by 3 determinant, which again is equal to the curl of the vector field f. So let's go ahead and find the curl of the vector field f, and then we'll talk about what it means, as well as show it graphically. So in this case, P is equal to 2z cosine x, Q is equal to 3z sine x, and R is equal to 5z. So the 3 by 3 determinant, again, is going to have the unit vectors in the first row. So we have I, J, K. In the second row, we have the differential operators, so the partial with respect to x, the partial with respect to y, and the partial with respect to z. In the third row, we have the x, y, and z components of the vector field. So we have 2z cosine x, 3z sine x, and 5z. And now using the expansion by minors method, to determine this first 2 by 2 determinant, we eliminate the row 1 column of the I vector, so we eliminate row 1 and column 1. These four elements make up this first 2 by 2 determinant. So we have the partial with respect to y, the partial with respect to z, and then we have 3z sine x and 5z times I minus, for this 2 by 2 determinant, we eliminate the row and column of the j vector, so we eliminate row 1 and column 2. The remaining elements make up this 2 by 2 determinant. So we have the partial with respect to x, partial with respect to z, 2z cosine x, 5z, times j plus, for this 2 by 2 determinant, we eliminate the row and column of the k vector, so we eliminate row 1 and column 3. So we have the partial with respect to x, the partial with respect to y, and then we have 2z cosine x, and 3z sine x. And now for each 2 by 2 determinant, we'll determine this partial derivative and then subtract this partial derivative. So for this first 2 by 2 determinant, we have the partial derivative of 5z with respect to y, that would be 0, minus the partial derivative of 3z sine x with respect to z, that would be 3 sine x, times I, minus the partial of 5z with respect to x, that would be 0, minus the partial of 2z cosine x with respect to z, which would be 2 cosine x, times j, plus the partial of 3z sine x with respect to x, which would be 3z cosine x, minus the partial of 2z cosine x with respect to y, which would be 0, times k. Let's write this in component form. So the curl of vector field f has an x component of negative 3 sine x, a y component of, notice how we have minus and then negative 2 cosine x, so it's positive 2 cosine x, comma, the z component is 3z cosine x. Before we go though, let's talk about what the curl of the vector field f means and look at it graphically. The curl of a vector field f measures the rotation or spinning effect. If the vector field f represents a velocity field of a fluid flow or windstorm, the curl measures a tendency of something to rotate in the fluid or wind. The curl of the vector field f points in the direction of the axis of rotation, and the magnitude represents the strength of the rotation or how fast it would rotate. The direction of rotation can be determined using the right-hand rule. Let's look at the graph of the vector field f as well as the graph of the curl of f. So here's the graph of the vector field f. So if we think of this as a velocity field, these gray vectors represent the direction and how fast the flow of the fluid or the wind would be moving. And now let's look at the curl of F. The vectors in this vector field, which is the curl of F, represent the tendency of something to rotate in the velocity field of vector field F, where the axis of rotation would point in the direction of these blue vectors, and the magnitude of each blue vector would represent how fast or how strong it would rotate. Let's take a look at both a velocity vector from the vector field F and a vector from the curl of F at this red point. So at this red point, the gray vector would be the velocity vector in the vector field F, and the blue vector would be a vector in the vector field, the curl of F. Where the gray vector would point in the direction this red object would move, and the magnitude of the gray vector would represent how fast it would move, and this blue vector, which is the curl of the vector field F at the red point, represents the tendency of this red point to rotate. It would rotate about an axis pointing in the direction of the blue vector, and the speed of rotation will be determined by the magnitude of the blue vector. Looking at this one more time, if this red point represented something in the vector field F, it would rotate about the axis pointing in the direction of this blue vector, which is the curl of F. And using the right-hand rule, if we point our right thumb in the direction of the blue vector and then close our right hand, it tells us the object would rotate in this direction here. I hope you found this helpful.